Welcome back, dear participants in MoroccoAI community. I hope you are enjoying the event, and I'm very happy to moderate the second session of today's conference with a very special speaker. For those of you who don't know our speaker, please allow me to introduce him to you. So, Merouane Debbah is a chief scientist at the Technology Innovation Institute in the United Arab Emirates. He is a full professor at Centrale Supélec in France. Prior to his current roles, Professor Debbah was the director of the Alcatel-Lucent Chair on Flexible Radio, and also he was the vice president on the Huawei France Research Center. Professor Debbah is a world-class researcher, and sorry, I cannot mention all his achievements, but let me just say that he received more than 25 Best Paper Awards and held more than 40 patents. In the wireless communication field, he is one of the pioneers of the small cells 4G and the massive MIMO technologies 5G. And today, he will be giving a talk about the challenges and opportunities of mobile AI. Professor Debbah, thank you for accepting our invitation. The floor is yours.
Thank you for the introduction. Let me just share my slides. Do you see my slides, yeah?
Yes.
Okay, now it's full screen. Hopefully everybody sees it. So first of all, it's a real pleasure to be with you, especially as I know many of the speakers here, and it's a great opportunity for me to interact with many of you. I hope next time I'll have the opportunity to come here. So it was quite difficult to find a title for my talk, and I wanted to at least tell you more about what's happening at the interface of AI and telecommunication. As far as I'm concerned, as today I'm working more and more on basically, of course, AI topics, especially here in Abu Dhabi, where we built the first what we call a large language model in Arabic called Noor. So LLMs and large language models are becoming a bit hype. I think if you have the time to go into chat GPT-3, for example, you'll have a bit of knowledge. What's missing is, of course, a lot of things which are very specific to the region, and this is exactly what we're building within here at the UAE. However, my topic was mostly to showcase you another domain where AI is having a big revolution, and that's related to telecommunication. And what I'm going to do is also give you a bit of background about how AI is seen from a telecommunication perspective and how it's impacting what we call 6G. So as far as I'm concerned, I think it was highlighted. I've been working at the interface of telecommunication and basically artificial intelligence. And I've been involved, of course, in many things related to industry and also related to academic realm, but also industrial, where I've been leading a lot of industrial centers these last years. So my talk will be on three parts. One is going to be about more general introduction on how AI has been at the heart of what we're doing, and then looking at two topics. One, which is basically on the topic of how AI is being used as of today to enhance the telecommunication domain. And the other is, of course, how basically telecommunication can, of course, provide a lot of things related to AI. So I think you're all familiar with what we call the G waves, especially for 2G, which was mostly for mobile for voice. And I think GSM, as you all know, was one of the big hype around what we call 2G. Around 2000, what we brought is something called 3G, which was mostly tailored for mobile for data. And as you can see, it's roughly a 10-year time frame. And then another thing that we built up in 2010 was mostly what we call 4G, which is basically providing mobile for internet. By the way, 4G was so focused on bringing mobile for internet that you have to know that voice or bringing voice quality is a big issue in 4G. Why? Because voice is considered typically as an application, but not a technology. And when you deploy 4G systems in general, calling is through what we call an app. And one of the apps is called Voice over LTE. And why I'm mentioning that is because I've been working intensively on 4G. And one of the big things that we had to do was improving the voice quality over a 4G system. And that's a quite difficult task to do. I spent a couple of years working on that in the sense that when you look at voice, what we call voice over LTE, voice over IP, it's an end-to-end metric, okay? What I mean by that is that even though you have a big number of bars on your phone, this is what we call the signal-to-noise ratio that you receive, it doesn't mean that the quality of your WhatsApp or voice over reality in that case is going to be good, because it depends on many other things. It depends on the protocols that you have behind, on the core network where the servers are, the IPsec protocols. And this is typically a case where I spent a couple of years trying to use modeling approaches that is usually used in telecommunication to solve that. And that never happened. And it turned out that around 2016-17, this is where I started to understand the potential of AI. Because many of the people working in telecom industry, I was very skeptical about AI in the sense that, well, you have good models. Why would you go for data-driven approaches where in the scientific realm, what you usually do is start with models and then you validate them with data. You're not going to create basically models out of the data. And I'm going to give you an example here, which is going to be very typical of the change of mindset that happened to me also on understanding the potential of using AI approaches. And by the way, the approach that we built is called AI-based voice over LTE and is actually deployed today in a majority of network. Said that, of course, we're arriving today with something around called 5G, which is tailored for what we call mobile for things, which is basically the IoT realm. But what's interesting today is that we're trying to build something called 6G by the year 2030, in a way we are understanding that AI is going to be pervasive, meaning you're going to have a lot of devices on which basically you're going to have AI on the edge. And one of the things that we're starting to think is what kind of basically standard or telecommunication infrastructure we're going to build, such as we can interconnect these different basically intelligence together. Of course, all the ideas I think you've been listening through this conference related to distributed AI, federated learning, things like that, are part of that. Because we know that the telecommunication industry is going towards a point where we don't want to transfer data from one point to the other point, because basically that's useless. You have a bandwidth which is used, you have problems of privacy because you're pouring data out of the smartphone, and you have coverage issues. What you want to do is transfer basically what is learned from one point to the other point and interconnect basically the knowledges, not the data. And this is, of course, how you start building an infrastructure which basically helps you interconnecting basically the models. And of course, federated learning is part of that. And all these stories are starting to have an impact today in the telecommunication industry. And today, of course, in terms of standardization, we're trying not to understand how we standardize AI, but how we standardize what we call the interfaces. What are basically the number of weights we're going to transfer from one point to the other point? What is basically how often you're going to do that? What is basically the point where you're going to ping that for doing that? And this is the discussions we're having today. Now, before I start talking about this whole realm which is happening in our industry, I'd like to say a couple of things on the interconnection between AI and telecom historically. So, of course, the first thing we can ask ourselves is, if we go to the father of telecommunication, is what did Shannon say about AI? Well, there's a very good paper that I strongly encourage you to read, which was published in 1949. It's called Programming a Computer for Playing Chess. And many of you maybe don't know, but Shannon was a good chess player, besides, of course, writing his two landmark papers, one related to information theory and the other related to secrecy of systems. And in the third series of paper, he wrote what he thought about the future. And interestingly, in that paper, he writes down what is happening today in the telecommunication industry with the use of AI. He talks about building machines for designing filters and equalizers. This is exactly what's happening today with what we call the autoencoders approach for doing better precoders or equalizers in communications. Machines for designing relays and switching circuits. Machines which will handle routings of telephone calls based on the individual circumstances rather than by fixed patterns. And today, of course, we are using basically AI to route basically calls. Machines performing symbolic mathematical operation, and as you can see, until magic machines capable of logical deduction. So of course you can ask me, why did Shannon, who had already all these ideas of using AI to increase the performance of telecommunication, did not use them? Well, it's exactly what's happening today. If you read at the conclusion, he gives exactly the example of chess and showcases that the computing power that we had in 1949 was not capable of doing all these things at once. And of course, a human is much more capable. On the second, of course, point is, what does also Shannon say about using networks for AI? not just using AI to build better networks, but how could networks enhance AI? And in fact, in the same reel, he builds another in his book with Weaver, talks also basically about the fact that at one point, telecommunication is not going to be about just being able to transport basically information from one point to the other point. Telecommunication in the future is going to be about transporting knowledge from one point to the other point to create between different points what we call common understanding. This is called, by the way, today semantic communication, and is at the heart of one of the points that he calls level B. And I think it's very important to highlight that the whole realm that we're seeing today, also in terms of what are the kind of infrastructure that we can build to transport not anymore information but knowledge, meaning some kind of extraction that you do through a model, is also one of the features that he highlights in his book, basically related to Weaver. Another thing also I want to mention is learning. Learning is also not new in wireless communications. This dates back to the book of Robert Wiener, which many of you may know as the father of the signal processing realm. And of course, in the signal processing, basically the idea is that whenever you don't have a model of your environment, which is exactly what's happening today, then what you will define is some kind of metric, utility function, or some kind of minimization of error that you're going to define. At that time, it was called the MMSE. Today, we call it the quality of service. And then through a process called feedback, you will try to shape your input such as you target your output. Of course, in control theory, everybody knows this, but exactly the idea is that you will be able to reinforce basically your input by a strategy. Of course, in wireless communication, we've been using these strategies, especially for people here who are familiar with Wi-Fi. In the Wi-Fi setting, for example, what we do is that you transmit at a rate towards your access point. In general, the packet is lost. If the packet is lost, then you have what we call a NAC. A NAC, it means that your packet is not acknowledged, and that the transmitter, what you're going to do is change your strategy, either by changing your power, either by changing the kind of rate at which you transmit. And by these kind of loops, you can basically many times converge to a certain point. And of course, in wireless, people have been using many of these algorithms related to that. This goes back from best response dynamics, fictitious display, reinforcement learning, joint utility strategy learning, trial and error learning, regret matching learning, Q learning, multi-arm bandits, and imitation learning. And all these kind of algorithms have been used. And what's also good about these algorithms is that we can show, in many cases, their convergence properties. And even if they don't converge, we can make them converge by changing the utility function. What I mean by that is if the utility function that you want to optimize does not have the right properties, in general, what you want as properties is that they're convex, then what you're going to do is that you're going to convexify that utility. In basically mathematics, how you convexify utility is by taking an expectation. And so you take an expected value or a mean value of your utility, and then by taking an expected utility, you can showcase that your system will converge to the right point that you have mentioned. Of course, the kind of strategy that you're going to use is going to be different. Instead of looking at a choice of rate or a choice of power, you're going to choose a vector of probabilities, and you're going to choose a certain rate with a certain probability, and you're going to show this convergence. Now, of course, these kind of algorithms have been used in the late 90s and 2000, and even 2010. I've been working intensively on that, and even looking at game theoretic approaches for that. And the whole framework is called, by the way, SON. SON means self-organized networks, if you're familiar with that, meaning you want networks, basically different access points, which will totally organize by themselves and find what are the right kind of power, frequency, and things like that they're going to choose. For people who have been working in cognitive radio, that's also part of that. Now, one of the reasons that it never made a success is that we realized quite rapidly that we have a problem here of what we call exploration versus exploitation. Meaning the problems of all the algorithms that I'm citing here is that by the time you converge, it's too late to exploit. And the reason is that you're in a mobile environment where people move. And so speeding the convergence was a big problem that we never were able to solve, only by reducing the space that we will explore, meaning instead of looking at a network, we're looking at just two users, two access points, which is quite limited. Of course, now we're realizing that by using not reinforcement learning, but deep reinforcement learning, adding the component where basically we're exploiting the memory and the computing, meaning that we will take a timestamp of the past, and whatever we gathered as information in the past, we will store it, create a model that will speed up, of course, our convergence. Because whenever we start a problem, we will not learn from scratch. We learn from all the past experience. And we know, for example, that if we are in a university and it's 8 o'clock in the morning, there may be not enough people, so there's no problem, and we can look back at the strategies that we've been using, and this speeds up the convergence. So the notion of deep here, usually what it does is that it speeds up a lot of the convergence time that we're talking about. And of course, this today is we're able to re-exploit, by the way, all the algorithms that I'm mentioning with the deep nature. It's called, by the way, today AI-based self-organized network, because there's been a change of paradigm where instead of looking at the classical Shannon point of view, where we have just a transmitter receiver, we're exploiting two new features here. The features that we're exploiting is the fact that in our devices, there's a lot of memory. So we can store all the data of my past communication. And then we can compute out of that past communication some models that we will exploit for faster convergence. Also, the type of communication that we do related to the Shannon level B type of communication that we're asking, we're also changing a lot of things. If you remember, in the classical communication system, whenever you talk to somebody, what you told him is deleted. So there's no kind of common understanding that you're building. Whereas we know that we as humans, the more we talk, the less we need to talk after. Because basically the person, you know what it has stored and has a model of the type of communication that you're doing. Of course, this is changing a lot of things that we're doing today through this notion that I was mentioning called semantic. Now, of course, I think the previous speakers have told you before why now, and I think these levels of winters that we went through are now providing us, of course, great capability with these three things that were posted many times, which are basically the huge amount of data, the huge basically amount of GPUs that we're having, and also basically the new type of algorithms that we're building, which have very sophisticated features. Although I have to mention, my experience working a lot in industry has showcased that a big majority of algorithms that we're using today still date back from the 90s. Of course, you can also always go from a gradient descent to a stochastic gradient descent or an epsilon one. There's some little tricks that you're building. But let's see the big majority of algorithms, I think there hasn't been a big type of big breakthrough which has been made since the algorithms of the 90s, which are basically the ones used today. And I think these three guys, and especially Jeffrey Hinton, who gave basically the initial speech in terms of introduction. And as you know, these guys today are roughly considered as superstars, meaning that whenever they give a speech, you have basically thousands of people listening to what they tell in terms of their work. However, what I want to mention is three things, which I think maybe have not been pointed out too deeply by my previous speakers. And for this, I'm going to give you a very simple example to understand where we are today. That's for my introduction, and where we should go. And I think this example is very good because it gives the opportunity to all the people who are listening to me, either they're specialists in AI or not, to get a grasp on how basically the telecommunication industry has been seeing AI. So you have two examples here. One is a guy called Newton on the right, and the other is basically what we call a ballistic kick. I'm giving you a ballistic kick example because this is an example that we use in wireless communication related to what we call beamforming, meaning you try to launch a beam with a certain basically angle and find where you will beam your antenna to be able to get that data towards the users. And creating that beam is extremely important because you need to find what kind of angle you will transmit to the user. So there you have two options. Is either Newton. In our case, basically, Maxwell equations, you know what is a precoder, you know the frequency, and basically you solve that. And in the example I gave you, you can find basically the angle which we can kick the ball. Second is, of course, you have no knowledge about what is a telecommunication network. And in this case, what you do, well, you go to the data-driven approach. So you kick the ball like hell. And so by kicking the ball like hell, you put two columns, one called distance and the other called angle. And you start stacking all these distances and angles. Next time you're asked to kick the ball at a given distance, let's say 100 meters, well, basically what you're going to do, you're going to check if 100 meters is exactly in your database. And if it's there, then you find the angle and you solve the problem. This has nothing to do with AI. It's called data mining. You still need to find some sophisticated algorithm to run fast your search, because you're not going to search 1 meter, 2 meter, 3 meter. You're going to cluster your data and say 100 meter is in the class 90, 110, for example. And within 2 search or 3 search, you can find the distance. Where you will talk about AI, but in fact you're going to talk about regression, is when the distance is not there. So if the distance is not there, it seems obvious for all of you that you're going to do some kind of linear regression between 90 and 110 if those were the distance were there. And then you're going to do a linear regression in the angle domain to find that distance. And then you have been able to solve the problem of kicking the ball without knowing Newton. In the telecommunication industry, for which I've been working for a couple of years, well, you're going to do the same. You're going to beam to many user equipment where user is, and you're going to put beam position, beam position, beam position. And next time there's a new user with a given position, you can interpolate between the beams and you're able to beam to the user without knowing what is the frequency, what is the layout, what is a precoder, and things like that. So it sounds like magic, and it's a bit like magic, by the way. However, I think here it's important to understand the 3 caveats. The first caveat is I went too fast. I went too fast because I told you that there was a one-to-one mapping between distance and angle. In fact, it's wrong. The initial speed is also important. So in fact, theta is a function of x and v0. Knowing the input-output parameters is a big problem today. It's not evident, and you need to have a bit of a hint on how to solve the problem. The same case for our industry, knowing basically what are the input-output parameters. It is as if I was telling you today that you are working in a startup of health. You go see basically the doctor, and the doctor goes see the data scientist and tells him, look, you have 2 columns. One is cancer, and the other is basically temperature. Now I give you new temperature, tell me who has a cancer. It's obvious you cannot do it. However, which column you're going to use is a big question we have in our telecom industry. Second thing, which I went too fast, is that it costs a lot. And we need to understand that the cost of these methods for the telecom industry costs a lot. In the example I gave you is that you can kick the ball many times. However, when you go and kick the ball when there's a wind of 10 kilometers, whatever you kick the ball when it was sunny would not work because you didn't go into the 10 kilometers I was talking about. So you need to kick the ball when it's 5 kilometers an hour, when the wind is 5 kilometers an hour, 10 kilometers an hour, 16 kilometers an hour, 18 kilometers an hour. Of course, you can always use techniques like transfer learning, meaning what you learn in one domain, you need less, but still it costs a lot. Typical example I give you, we start building an infrastructure in Paris. Then we decide to build the network where we train basically the different base station in terms of learning how to beam and other parameters. We took those parameters and go to Casablanca, for example. While Casablanca has a very different kind of topology in terms of building than Paris. So you need to learn there again. And once you go from there and you want to go, for example, in Abu Dhabi has also a different layout. So of course, you can always do some transfer learning, meaning you will take your initialized parameters that you optimize in Casablanca to start basically your network there. But it's still the amount of things that you need to do is huge compared to a model that you would have. And the third, of course, caveat of this technique is something which is quite known, is the fact that whatever kicking the ball that you can do on Earth, you'll never be able to kick on the moon. So of course, this has nothing to do with AI. We all know that. It has to do with the fact that the kind of techniques that we're using are mostly based on classification methods. We know that to solve that problem, we need to use more topological structures. geometrical structures, which try to find not a class, but try to find what we call invariants in your data, meaning what are the invariants by rotation, by translation. Because here, basically, if you want to learn gravity, gravity is an invariant. We know that. And so you need to find basically some mathematical structure which are only based on the fact that you can build up some invariants in your data. Okay? Another question also that I think is very important, of course, there are domains where we know that these techniques work, and this is why nobody questions that. And of course, I think many of you were doing PhDs in the 80s, and in the 80s, whenever you did a PhD in speech recognition, you spent time modeling the larynx here, meaning how the sound is emitted. It never worked, meaning modeling never worked. And today we realize that doing speech recognition has nothing to do with models, but it's a classification problem. We got a huge hit in that discipline in terms of doing. So of course, we have disciplines where we know that this is where the way to go, but we know also the limitation. And the last example I want to give also to the audience, especially in those who are coming in the academic realm, is related to the data. And I think this also is a big issue in the sense that many of the people I speak to in general tell me, look, industry has an advantage compared to academia because they have the data, and this is why we see all these outstanding publications in big conferences like NeurIPS coming more from the classical companies working in software and not academia because they don't have the data. And then of course academia comes and complain about the fact that, well, you should share your data and give it to us. And in general, the answer that is given by industry, and I've been one of them, is, oh, we cannot give you basically data because it's an issue of privacy. We have customers, and if we reveal their data, then will be big stuff. I think this is one part of the story. The truth part of the story is this example, which is quite known in statistics. So here you have what we call an airplane, and this is the classical type of airplane that we had during Second World War, where these planes were parked in the UK and going to Europe to bombard basically German sites, and then coming back to the UK. And the red dots that you find there is what we call basically the bullets, which were shot by the Germans on the plane. And the commander of the base at that time was asking basically the statisticians, you can call them data scientists today, well, tell me where we should reinforce the plane. And so, of course, it's obvious when you look at this picture that you should reinforce the plane where there are many red dots. So you can find basically the kind of amount of metal that you need to put on the wings, on the central, so that you can protect it from the shots whenever it goes back. And of course, the pilots came in and said, no, you're totally wrong, guys. It doesn't work like that. You should put more metal where there's no red dots. So why would you put more metal where there's no red dots? Well, because on the cockpit that you see here, this is exactly where the Germans were shooting the plane, and those planes never came back. So what I mean here is that we had missing data, meaning that the data scientists were working on data which was missing because they didn't know that there were some planes which were missing. And so one of the things that you need to know is that if we start revealing what is missing in terms of data, well, you start providing more and more information to the people. So as when you're a company, in general, if you want to reveal the whole process of what happened and how you generate the data, you start revealing know-how. And the know-how is key for a company. You cannot start revealing it outside. So one of the reasons that people need to be very careful about is that you can always find ways through NDAs and things like that to protect yourself from basically all the data leakage. However, if you start basically providing the know-how outside, then you lose all your capability because that's exactly how engineers work, and you don't want to reveal that outside. And I think this is a very important point that we need to solve at one point to be able to have basically our academics working more with the data which is generated by industry. Now, of course, this was a general introduction that I gave. I'm going to go on the core of the topic a bit fast. Sorry, I needed to spend a bit of time to showcase you, of course, what we're doing today with all the ideas I've been mentioning. Not going in all these different directions, but just giving you a hint of what we're doing. So let's start basically with the first part that I was mentioning, which is basically using AI for better networks. So as I told you at the beginning, one of the big problems that I had at the start of trying to improve basically the quality of voice on a 4G network is that I spent a lot of time trying to model the end-to-end metric and never worked. And it's until in my former company, the business units came to see me and told me, well, Merouane, we have a lot of data of different network and different voice over LTE quality, or you can call it voice over IP. By the way, LTE is the technology behind 4G. It's called long-term evolution for people who are not familiar with that. But for voice over LTE, which is the WhatsApp, if you want, of basically 4G, well, we had a lot of different basically topological structure in terms of where the base station were in different networks that we built with a different voice over LTE. But then I said to myself, well, this is great because now if you fix me the voice over LTE kind of KPIs that you want in different networks, I can find by using some spatial regression what will be the right topology that we can do. So we worked on that. This is called AI-based voice over LTE. And as you can see, the kind of improvement that we got in the downlink and uplink are roughly around more than 80% and 20%, for which basically no technique related to models were able to achieve because we had a problem of end-to-end metric that we need to do. And this, of course, changed my mind. It also changed a lot of things in the industry and looking at the fact that AI has basically some capability in terms of improving the system. And when you look at the value, instead of looking at the link, you look at the data. The scenario, instead of looking at manually, you look at it automatically. The target is a global probability optimization. This is very important, rather than a local predetermined optimization. It's an end-to-end network, and it's not a local point that you're trying to model. And you're looking, and you just set the targets. And you can see, depending on the execution time, you're working at the resource block or the slice, you have different application. And these today are going in all directions in our industry. It goes from pure physical layer problems related to what we call peak to average power ratio nonlinear compensation for people who are working on WebTM, to LTE power control, to things which are more at the RAN AI chipset and AI base station, going from regression clustering classification to reinforcement learning, dynamic optimization, to deep learning, reinforcement deep learning, transfer learning, graphical algorithms. And as you can see also, it helps today improving the network operation and management to network performance that I was talking about, voice over LTE, but also things like TCP optimization to predict also write requests and high accuracy localization. There's a couple of examples I could go through. I'm not going to go across all of them. The first one I told you about was about this AI-based massive MIMO, where you can find the beam pattern, which is optimized based on the UE localization. And for a base station, optimizing that is extremely complicated, and for which you can have a reduction based on the fact that you're using AI techniques. Two, I'll jump also on that, to things also that have been in the feature a lot in terms of localization. In terms of localization, as you all know, especially in indoor environments, when you don't have satellite coverage, it's extremely difficult to localize. In this domain, you have to know that many years people have been trying to use what we call fingerprinting approaches. What are fingerprinting approaches? It means that you measure what we call the spatial signature of a user towards multiple base stations. So it's not the delay. Careful. It's really the signal physical signature, meaning Maxwell equation signature that you see on your antenna structure. And then basically you put UE location, antenna, basically spatial signature. UE location, spatial signature. And next time you see a spatial signature, then of course you try and infer where the UE is based on what you have. So usually this was done based on data mining approaches. It didn't work. And as of today, of course, we're using techniques based on deep learning to do what we call AI-based localization, where we can still recover the localization by using basically consistency approaches, where basically we try to find what is consistent in the kind of signature that you have, even though things have changed. What have changed, basically, some people have moved in the room and things like that. And the accuracy today is quite good in terms of what we call AI-based localization. It's also used at the level of real physical layer to improve basically the coding schemes The decoding structure when you're transmitting an information is quite complex. Today, people are using trained decoder based on AI to improve the performance. Here you have a couple of examples. It's also used basically to do resource allocation and transmission systems, and also using multi-agent reinforcement learning to be able to find what are the kind of resource allocation, power, HARQ decision mechanism that you need to do when you start learning. By the way, maybe I didn't mention it, but at the heart of the improvement that we saw these last years in communication, feedback was key, meaning that whenever you transmit to a user, the user gets you back a feedback. The feedback means that he acknowledges or he doesn't acknowledge, but it could be with a better granularity above that. But now what I want to talk about is where I think telecom has an impact on AI. Because all the talks I've been seeing before mine was mostly about how AI is great, how AI is improving system, how we can make AI better. Here, the idea is that AI in the future will be distributed. And we need a network or a computer or a distributed computer which interconnects all these systems. And it interconnects them to make basically this distributed AI much better than basically a more centralized AI because of the constraints we're having. And so, of course, the problem started many years ago in the telecom industry, where we realized that we're overflooding the network with a lot of data which is stored from the phones towards basically the core network. In terms of backhauling, the system is not able to sustain that. Okay? And so we realized quite rapidly that you don't need to bring everything. You just need to bring what you need. And then second, we realized also that many constraints imposes us that we cannot basically take decisions quite fast if we bring all the data. One is latency. Autonomous cars is one. The kind of latency that is required, we're talking about roughly 1 millisecond. So by the time information goes and comes back, it's too late. So things have to be done locally. Second is, of course, the big question of privacy, which is coming back and again in terms of, I don't want my data to go out. You can learn from me, but I don't want my data to move out from me. And the third one is, of course, also the problems of coverage, which basically requires that sometimes your systems still need to be smart, but not connected to the cloud. Typically, you're on an airplane. In an airplane, you're what we call on a airplane mode. In airplane mode, your systems needs to continue to work. And so the question is, what are basically the kind of architecture that we can build so we can have what we call unified training and inference framework, such as you can have a device, edge, and cloud to make the whole system work, in which you're going to be able to provide what I call this technology, which we will stamp here in our case as a 6G technology, which enables you to interconnect basically this different system together at the speed and the scale that you need. What I mean by scale is that imagine 1,000 devices for which you need to learn quite rapidly, immediately, everything. Okay? If you use federated learning approaches, if some of the people are familiar with that, if you start hopping one after the other, it's quite too late before you get information. Because if you start putting your model from one device to the other device, then the other device to the other device, and then you go on like that, you can't. So you need to think about how you cluster all these IDs. And of course, this is doable because the whole industry is jumping towards making basically devices which can work more and more on the edge. And here you have a couple of figures which you can find today on internet, which provides you the kind of capability that goes from an earphone to a data center, and which showcases you that you can do inference. And of course, today people are pushing things like training. On the training part, by the way, I need to mention that this is a quite interesting framework for people who are interested, where we're trying to build a lot of what we call low precision AI. Meaning, maybe some of you saw the first talk today. Well, when you have a neural network, you have weights and layers. Those weights, if they're continuous, you can do a gradient. However, if you start lowering the precision of those weights to say to be binary, they could be quaternary if you want. But if they're binary, then you cannot learn anymore, because learning basically is optimization, and optimization requires a derivative. And you cannot do a derivative when you have weights which can only take 0 and 1. So you need to reconsider how you will do basically a neural network on which you have weights which can only take 0 and 1s. Binary neural networks are part of that, by the way, where basically you need to come up with a new type of algorithms. And of course, for people who are here, I think they're quite familiar with that, because if I tell you how you can optimize a system in which you constrain your inputs to be only 0 and 1, well, it's combinatorial optimization. So the problem of learning becomes a combinatorial optimization problem. And the combinatorial optimization problem, the gates are wide open, as you all know, to many heuristics. Because when you do combinatorial optimization, we know it becomes an NP-complete problem. And there you need to reduce the scope and find basic heuristics to do that. And I think this is a very interesting, I would say, trend of research today, not doing just inference, but also doing training and inference directly on the device. And of course, this has an impact on the kind of network that you build. And as you can see here, as of today, the networks that we're building are very centralized with the central AI, on which you have devices on the bottom. They provide the data, it goes up, you create a model, the model is then shipped to all the devices, and then you start working with them a couple of times and going up to something which, from my point of view, is still not the best structure, but for which we're converging, where you have a terminal AI, a site AI, edge AI, a cloud AI, and all these interfaces talking to each other in terms of exchanging, basically, as I told you before, the model, and for which you need to standardize the interfaces for talking to each other. Again, you'll never standardize AI, you'll standardize the interfaces on which these different, I would say, intelligent entities will be talking to each other. Again, why I was mentioning that I think it's not the way to go is that I think we didn't take the problem at heart of understanding if AI is pervasive, what would be the kind of network which would be optimal to infer on a parameter? And I give you just an example. You can ask yourself, why did we build cellular networks? Well, it's quite easy to explain. If you want to build a network to communicate from one point to another point in Morocco, for example, you can show mathematically that if you decide to do, for example, an ad hoc network or any type of network, the system does not scale because you'll have what we call problem of interference. And it was shown that the best way to transmit from Casablanca to Agadir, for example, would be to build a network where you cut the system into pieces. In each piece, you have what we call cluster head, base station in your case, where all the users in that communicate with cluster head, and it's the cluster head which communicate to the nearest cluster head where your intended user is, and from that cluster head, you communicate to the user. And this is exactly what a cellular network does. Because if you start communicating randomly and sending your data by hops, this is called other, whatever, the system will break down and does not scale because of this interference generated by your system. And here again, I think we haven't spent time in saying, if I have AI nearly everywhere, how am I going to organize my system? Such as I optimize the spatial layout and the protocol layout, such as I can do what an AI task will do at the end, meaning infer. Infer meaning it can be sensing, it can be localizing, it can be many things in your system, by the way. Of course, all these ideas are still going through, and I've been working also with a couple of colleagues, ex-PhD students, around these things, about looking, of course, on these distributed structure that you can work, going from federated to collaborative, and looking at these two problems that I've been mentioning here quite extensively, going on the two aspects is AI for a better network and network for a better AI. And I think the big potential today, AI for a better network, I think is going to be there for a couple of years still. The low-hanging fruits, from my point of view, have been solved. It's more, as I told you, the problems which are more tougher, on which you go on things which are above, basically, the classical realm of just using these techniques of deep neural networks, and for which we're going to solve this. By the way, I didn't mention is that also the LLM realm, I think some of you have been talking about this, what we call the large language models, are also coming around here in the sense that we don't want to build basically any more AI models which solve specific tasks, but we want to build basically models which are good at many tasks at the same time. So we don't want something extremely good for one task, but we want something good for as many tasks as we want, going from cybersecurity. So a lot of companies are starting to build up what we call here the telecom brain, by the way, in terms of crashing all the data to solve at once. But the other thing which I think is going to have a huge impact in 6G is this network for better AI. I think I'll stop here. I had one or two more slides, but I want to spend like the next 9 or 8 minutes answering some of the questions of the audience related to that. Thank you again.
Thank you, Professor Debbah. If you can just stop sharing your screen. Thank you again, Professor Debbah, for this talk. It was really insightful, especially for people who want to know the evolution of communication system from Claude Shannon until actually currently the approach based on data. So we have now a lot of questions from our community, and maybe I will be sharing a few of them. So for the first question, during your presentation, you have talked about the G waves, and it seems that each technology takes about 10 years to evolve from a generation to another one. And between those generations, there are small steps taking place. We've already heard about 4.5G, 4.6G. So the question here is how the technology is currently evolving before arriving to 6G. How does the 5.x look like?
That's a good question. So today we're deploying in the majority of network what we call 5G, which is three things, which at least permits three things. One is basically what we call the evolved mobile broadband, meaning better rates, 10 to 20 gigabits per second. The other is what we call ultra reliable low latency communication, meaning providing a latency of roughly 1 millisecond. And the third one is what we call the massive machine type communication, meaning being able to connect roughly 1 million objects per kilometer square. So that's what 5G is bringing in. By 2025, we're building already what we call 5.5G. So that's a good question. In 5.5G, we're adding three new features. One is basically the combination of massive connectivity and mobile broadband, having basically uplink-centric communication, meaning there's a lot of cameras that are being deployed. The massive connectivity today is mostly related to IoT, which are sending tweets. And we're tackling the problem of having a massive connectivity with high data rate to pour all the cameras data up to the base station. Second thing is what we call basically the possibility to combine high data rates with extremely reliability. It's called UCBC. And this is a big problem for VR and AR, okay? So VR and AR requires high data rate and extreme reliability. And the third one, which is the premises of 6G, is the fact that we're seeing today already a big need for 5.5G to provide basically sensing capabilities and localization capabilities. So typically LiDARs, so wave usually is used only to transmit data. Today, we are getting a lot of requirements to use wave because we're starting to use millimeter wave frequencies to be able to see our environment. So what equips car, for example, today are LiDARs. It's like radars that you put in your car and enables you to move around. So this is a lot of things that are now putting forward in our industry to be able to do better sensing of your environment. So this is what's going to happen in 5.5G. And it's already in the roadmap of release 19, if the person is interested by that, and being discussed to move towards that.
Amazing. So we can move on to the second question. And maybe the second question is about connected things and connected intelligence. When we have presented the first concept of communication system proposed by Claude Shannon, 1948. So the question here is how it is evolving now, these systems to Shannon 2.0 with the new added component of learning at the receiver. In fact, here the question is, what are the biggest challenges facing the data-driven approaches in mobile communication?
So there are two things here. So the Shannon 2.0 is mostly about the shift that we're seeing today and the fact that since memory is key and computing is key, In the Shannon point of view, initial, we don't basically store the past data. So basically, what you send is forgotten in some sense. Okay, so what you send in general is information, but you're not sending basically what you already know. In general, today we know that if you send a lot of data to your receiver, there's already some stored data which has been done, and there's a model that you can create. So there's things you don't need to transmit anymore. This is called semantic communication. I'm not quite sure we'll make it, by the way, for 6G, because I think we're starting to develop only the theory and not basically still the code structures or whatever for that. So I think we're quite far from having semantic communication happening. But the fact that we have basically data which is transmitted in the past is a big change.
Amazing. So maybe I will finish with the last question, and this is a more general question. So Professor Debbah, you have been working for a long time in different academic institutions and industrial ones. So you are maybe better placed to share with us your thought about research in academia and industry. In fact, in the era of AI, and more specifically in data-driven approaches, we are moving now from fundamental scientific research in academia to more applied research in industry. What are your thoughts about this transition, and do you agree with that?
Yeah, so I think this is a very good point. I think academia, I mean, my experience from moving from one point to the other point is that academia should not, let's say, adapt too much to basically. So what's the beauty of academia is that academic people have time to think. They have time basically to look at crazy ideas, and they have also the freedom to fail, which you don't have in industry. And I think the kind of research that academia needs to do is mostly on what I call science-driven and a bit of technology-driven research. Technology-driven is also important, meaning they look at what's happening on the problem. Industry has to do what we call business-driven research and technology-driven research. And I think the mix between both can be in this technology-driven research because there's a lot of things that academia can do and a lot of interesting problems that industry would do. However, on the business-driven approaches, meaning problems, things, I think academia does not need to interfere in the sense that there are already good people in industry, and this is not where academia is looked at as being good. I think academia should still like push and guide industry on what are the problems that we need to solve within the next 10 years and prepare basically for. I give you an example. In industry, I've been working and I mean, like hell. And then basically people tell me, okay, we have to start 6G research. And when we start 6G research, we start looking at the papers that was in 2019, 2020. There was nothing. And that's not good because you should be the ones preparing already the future and having already some disruptive technologies on which we will jump in and make the engineering of it. And I can give you a very good example in my previous company. We were able to bring what we call polar codes in the 5G standard because we found a very good paper, which was published by Erdal Arikan in 2008, which was there, which was more the Telcode level. But that was very good because that's his work. And then we started implementing that and making an engineering flavor of that. And I think this is where things should be a bit separate, is science-driven academia, business-driven, and in the middle you have technology-driven. Now there's a question for you guys in academia, of course, is the data. This is something I've been moving around, I haven't solved yet, and I gave you exactly what I thought about it in my presentation.
Yes, that was the last question, but I would like just to relate your answer with the evolution of a communication system. I think that Claude Shannon, for example, in 1948, when he published his famous paper about information theory, the application of those concepts appeared quite later. And I think at that time we have started with theory to move on to the applications. But now we are dealing with first the practical applications and looking afterwards to the theory behind. So I'm really afraid that it could have an impact on science itself. What do you think, Professor?
This is what I'm saying, is that I think I'm seeing a bit of mixture, which I think is not correct, is that academia should still push basically for science-driven research, meaning creating the new theories on which we will do the applications. It doesn't mean that you cannot basically work on technology-driven problems. problems. That's what even Shannon does. You know, when Shannon was employed in the 1940s at Bell Labs, they had also some tasks to work on radars, you know, improving the radar systems, things like that. But I think this should be a part which is quite small compared to what you have to do. You need to do it because you need to be connected with the world, especially when we request your help. Because on some of the problems, you are the best. Where in industry, you don't have the people who have time to dig deep in those problems. But that shouldn't take you all your time, because otherwise it will also fire back on industry. You understand what I'm saying? We'll fire back on industry because I don't have no clue what's going to be 7G. So if you don't start thinking about 7G, once we have our head fully done with 6G, when we raise up, we have no clue how to move forward. So we'll be spending time on trying to find some new solutions that you may have already put forward.
Yes. So maybe if you can just give a last word to our community MoroccoAI, it would be good if you give it in French. Un dernier mot, Monsieur Debbah, à notre communauté.
J'étais très heureux d'être ici avec vous. Je partage beaucoup d'étudiants. Je tiens à insister que je pense qu'il y a une force assez importante de la communauté marocaine dans l'IA. Et ça, c'est principalement les aspects mathématiques. Je pense que sur ces aspects-là, je pense qu'il y a un énorme potentiel. Enfin, l'école mathématique marocaine est excellente. On le voit à travers les classements mondiaux et les classements également dans les grandes écoles, les classes préparatoires, etc. Et je pense que là, il y a un atout à jouer sur globalement trouver le prochain Hinton, lequin venant du Maroc, parce que c'est à portée de main. Beaucoup des problèmes qui sont aujourd'hui posés sont à portée de main de l'école marocaine, et en particulier sur ce que j'appellerais la troisième voie de l'IA, sur lequel tout le monde essaie de plancher, qui demande en fait des outils mathématiques assez sophistiqués.
Merci encore une fois, professeur Debbah, d'avoir accepté notre invitation et pour votre excellente présentation, et au plaisir de se voir très prochainement.
Merci.
Merci.